Find the weight of the cone in pounds force. In this problem, a cone rests at equilibrium and is in contact with three separate fluids: air, oil, and water. The specific gravity of the oil and water are provided. The depth of the cone, lowercase d, within each of these three fluids is identified using variables d1, d2, and d3. Also, the diameter of the cone is provided. To solve this problem, we'll begin by summing the forces in the vertical direction, which equals the buoyant force, Fb, minus the weight of the cone, W cone. Therefore, the weight of the cone equals the buoyant force. The buoyant force equals the sum of rho g v for the volume of all fluids displaced by the cone. This concept is sometimes referred to as Archimedes' principle. Therefore, the buoyant force includes a contribution from the water displaced by the cone and a contribution from the oil displaced by the cone. Also, the density of the fluid, rho I, equals the specific gravity of the fluid, Sgi, times the density of the water, rho W. After making this substitution for the densities of water and oil, our revised equation for the buoyant force is rewritten and simplified. The density of water equals 62.3 pounds mass per cubic foot. The gravitational acceleration constant equals 32.2 feet per second squared. And the problem statement provided the specific gravities of water and oil. This means we're left to compute the volume of the cone submerged in water, VW, and the volume of the cone submerged in oil, VO. The volume of the cone submerged in water, VW, equals the volume of a smaller cone having a height of lowercase d1 and having a diameter we'll define as uppercase d1. The volume of this cone equals 1/12 pi d1 squared d1. From the problem statement, we know lowercase d1 equals 4 feet. Uppercase d1, the diameter, can be computed using similar triangles, and noticing the diameter and height of the cone submerged in water is proportional to the diameter and height of the entire cone. After solving for diameter d1 and plugging in the given values, the diameter of this smaller cone equals 1.5 feet. Now we can solve for the volume of the cone submerged in water, which equals 2.356 feet cubed. At this point, the last unknown variable is the volume of the cone submerged in oil. To solve for this volume, we'll define variable uppercase D2 for the diameter of the cone at the oil-air interface. Now, we'll define VO as the volume of the cone with a diameter uppercase D2 minus the volume of the cone which is submerged in water, VW, which we just calculated. The only unknown variable is the diameter uppercase D2, which we can solve for, again, by recognizing the proportionality between this cone and the entire cone. After solving for diameter D2 and plugging in the known values, diameter D2 equals 2.25 feet. Now, if we plug in diameter D2, depth 2, depth 1, and VW, this makes the volume VO equal to 5.596 cubic feet. Lastly, we'll return to our equation for the buoyant force, Fb. And after plugging in the known variables, the buoyant force equals 14,717 pounds mass feet per second squared. After multiplying this value by a unit conversion, the buoyant force equals 457 pounds force, which we previously determined was the same as the weight of the cone. When reviewing the possible solutions, the answer is A.